Okay, should we start?
Yeah, let's start. Nazhan is there now? Nazhan, are you there?
I am here.
Okay, let's start. I'm the brother.
Okay. Bismillahirrahmanirrahim. Okay, we'll start by Sir Burhan's topics. First, we'll try to cover those, and at the end, we'll try to cover Sir Asif's. Because the course of Sir Asif is pretty much similar to the what we taught in the midterms. So that's if we have time, then we'll try to cover this. But Sir Burhan is pretty much different, so we'll start by this. Okay. So we have two topics of Sir Burhan. First one is pre-stress. We have to calculate the pre-stressing. Uh, and second one is UBC method. We have to design or check uh, our buildings by UBC. UBC stands for Uniform Building Code. So we have to check our existing building by this, that whether um, they will be safe when a screw strikes or not. It is actually of 97 from 1997. It has now become IBC, International Building Code, but we are still using UBC here in Pakistan. So we are being taught this. So first of all, pre-stress. So what is pre-stress? For example, this is a beam. This is a simple, suppose this is a simply supported beam. If we apply some load on it, some UDL suppose, if we apply some load, it will bend in this direction, right? It will bend in this direction. There will be tension at bottom and compression at top and compression at top. So the tension at bottom, we know that this the concrete, it's very weak in tension, right? It's very weak in tension. So the tension at bottom will produce cracks in it. At bottom there will be cracks in it. So to prevent this or to mitigate this, we try pre-stressing our concrete. Pre-stressing is simple concept, like if this is a concrete beam, we place a steel tendon or steel wire in it and we pull it on both sides. We apply some tension on the steel wire. But this will cause when we release this wire from the both ends, so our beam will hog in this direction like this. The strands of wire will try to come back because they are stretched, and when we will release, they will try to get back like this. So our beam will hog like this. So hogging causes tension at top and compression at bottom. So this is pre-stressed concrete. So if our load acts downwards, because all the gravity loads are acting downwards, so what will happen that instead of bending deflecting downwards, our beam will just come original position like this. There will be almost negligible tension at bottom, or even there will be compression at bottom. It depends on how much we have pre-stressed the concrete. So what is the benefit? That we are almost making the tension at the bottom of concrete almost zero. So this is why we pre-stress the concrete. It will obviously increase the capacity as there will less cracks. So our section would remain uncracked and it will increase the capacity of the concrete beam or whatever we are pre-stressing. So this is why we pre-stress the concrete. So we have to solve these numericals. For example, this is one in the assignment we were given. So before that, suppose there are two types of pre-stressing. Pre-stressing, we can do it by two types. First is pre-tensioning, and the second one is post-tensioning. Pre-tensioning, For example, if we have a mold of concrete, if we have a mold for concrete, and we haven't placed any concrete in it yet, we put the wires in it and pre-stress them, give them some tension, and then we place the concrete in it. We call it as pre-tensioning. That we stress the wires before placing the concrete in it. So it is pre-tensioning. Pre-tension. What is post-tensioning? We cast the concrete, we let it harden for 28 days or something. Then after it has fully hardened, we place wire nets and then we stress them. So after complete hardening of concrete, if we stress the wires, then we call that as post-tensioning. Is this fine? What is pre-tensioning and post-tensioning? Usually we stress the wires before casting in pre-tensioning, and after 3 days, 3 to 4 days, we release the wire after concrete has sufficiently hardened. So that stresses are transferred to concrete. In post-tensioning, after 28 days or something, we place the wires and stress them. So after we stress the wires and we release them, obviously some portion of the stressing force would be lost. For example, if we have stressed the wires to almost 100 kilonewton tension force, if we release them, some part of concrete it will behave elastically and it will shrink. Some part of the concrete will shrink. Yeah, and somewhere the steel bar will slip from the concrete. So some part of this pre-stressing force would be lost after we release it. So this we call it as PI before the release of uh, jacks or something. So we call that initial pre-stressing force. What we actually applied on the pre-stressing. And after we release it, so what would be transferred to concrete, we call it as pre-E, effective pre-stress force. That it will be after losses. This we applied it, PI we applied it, and after losses, what would be transferred to concrete, we call it as PE. So what are the type of losses? You can go through such like from here. Actually, uh, this came last time. This what numerical wasn't asked last time, but this theory part was asked that what are the type of losses in pre-stress? So these are instantaneous losses and time-dependent losses. This one time-dependent losses. So instantaneous occur exactly after we release the wire. They occur instantaneously. So they are due to loss of friction, that the bond between the concrete and the steel is somewhat lost. So this one due to anchorage and due to elastic shortening that occurs immediately. So time-dependent losses are due to shrinkage of concrete. This is due to after setting that water evaporates from the concrete and it leaves behind pores, and this causes shrinkage. After concrete tries to fill those pores, so this causes shrinkage in concrete. And due to creep, it is a long-term deformation and due to relaxation of steel. So these are time-dependent losses, and these were instantaneous. Uh, Try to memorize them because they might be asked. Last time it was all, so they're less access now, but it may be. So there are two types, P and initial pre-stress and effective pre-stress force. And that's it, I think. We should go to numerical. Yes, formula. So the formula for we'll try to go formula in the numerical. Okay, any problem up till now?
No, brother.
Okay, so we'll try to go through numerical. Okay, in this, it is saying that a rectangular concrete beam of width 11 inches and depth 28 inches. So we are given a concrete beam. We have 11 inches of width and 28 inches depth. 11 inches is width and 28 inches is depth. and post tension using a single parabolic tendon. So this is its longitudinal section. This was its cross section. So it is post tension. For example, this is the center of gravity of concrete. So it is post tension using a parabolic tendon. So I can draw a parabolic tendon like this, a curve. It has eccentricity at midspan. Its eccentricity at midspan, for example, this one at midspan E is equal to 7.8 inches. Eccentricity at midspan. And 0 at simple sports. So eccentricity here is 0. We do not need this, so this is not required. We only need eccentricity at midspan. Initial pre-stress force was 334 kips and effectiveness ratio was 0.84. Okay, initial force was EI was 334 kips. R was 0.84. R is it effectiveness ratio, or we can use it to calculate PE, effective pre-stress force. So that would be R times PI. This ratio multiplied by PI. So R indirectly shows how much losses have occurred. How much losses? Here almost 16% losses have occurred. So 0.84 times 334 kips. You can get PE, or effective pre-stress force, like this. Or is this superimposed dead and live loads of 300 and 1000? So WST, superimposed dead load, is 300 pounds per feet, and WL is live load of 1000 pounds per feet. So we can combine them as W is equal to 1300 pound per feet. So this is a superimposed load on the concrete beam. It is distributed uniformly, and the span is 40 feet. So we have span of 40 feet. This is concrete stand 5000 psi, and at the time of transfer, it was FCI was 4000 psi. So these are concrete stands. We'll use them shortly. Okay, this is all the data given in the question. So first, we have to calculate parameters. Calculate parameters. For example, this was the equation of pre-stress. This is F is the stress. It is P over A negative 1 minus P or plus PC over R square plus minus M over S. This is basic equation of pre-stress. So we require area of concrete for this. We require C for this, R square for this, and S for this. We require all these 4 parameters. So we have to calculate these first. So area of concrete, AC, simply 11 times 28. So 11 into 28, 280 and 300 and 308, I think. So this would be area of concrete. Second, we for radius of gyration, we require moment of inertia. So IC would be PD cube by 12. 11 into 28 cube by 12. So this is how we can calculate IC. Third, R. So we know R as I over A. R is I over A. So if we square both sides, we get R square as I over A simply. And we also require R square here. So simply, if we divide moment of inertia by area, we can calculate R square. And C is the distance from neutral axis of the member. So this is neutral axis to the top or bottom fiber. The top we call it as CT, and to the bottom we call it as CB. Because this is a rectangular beam, so neutral axis would lie at 14 inches, half of depth. So we'll have same CT and CB that would be also equal to 14 inches. So CT or CB all are equal and there are 14 inches. All right. And lastly, for section modulus, S is section modulus. S is equal to I over C. So moment inertia divided by this distance. So we'll get section modulus. And we also have two types of section modulus, ST for top, I over CT, and SB for bottom, I over CB. For irregular shapes, we'll have different values of CT and CB. So we have to calculate two different moments of inertia, ST and FB, SB. But here, since this is a rectangular section and regular, so we have same values. Okay, so these values we have calculated. Last thing is left moment. So first case is for initial condition before application of load. We have to calculate Plagiar stress distribution before load application. So before load, superimposed load. So before load, we have top stress and we have to calculate bottom stress. We have to calculate top and bottom stress in every case. So for before load is applied, so we have to calculate top and bottom, and we have to use PI for this. PI. That it is before the application of load, so it would be before the losses. So we have to use initial pre-stress force. This is before the application of load. PI over AC. This is with negative sign because it is in compression. For top, it is 1 minus EC over R square. For bottom, it is 1 plus EC over R square. This sign difference is here, 1 minus and 1 plus. And since the moment, for example, this moment, if we apply some load on it beam, this moment will produce sag in it beam. For sag, there is tension at bottom and compression at top. So we write compression as negative. So we'll write as minus M over S. Why? Because it is this load is producing compression at top. So if we are writing stress at top, we'll write it as minus M over S. It is producing compression at top. Similarly, it is producing tension at bottom. So plus M over S. And this is S, this is MD. That moment. Okay. This is how we have to write the equation. And for MD, we know that unit weight of concrete gamma is equal to 150 pound per cubic feet. We have to memorize this. It is 150 pound per cubic feet or 25 kilonewtons per meter cube. Whichever the units are. So these are the unit weights. And if we multiply this unit weight with the area of section, this area, if we multiply this unit weight with the area, we'll get dead UDL, gamma times area. So for example, 150 times 308 will get UDL, which is the self weight of this pre-stressed concrete. This is actually the self weight. WD is the self weight of the pre-stressed concrete. So for this moment, we can calculate omega L square over 8. So simply multiply WD with the square of span. Span was 40 feet and divide by 8. So we'll get the dead moment. So after plugging the values, we know MD, we know S, EC, R square, we know, and PI and AC we know. So if we plug in the values, we can calculate stress as top and we can calculate stress at bottom. This is before the application of service load. So any issue up till so? Or is it fine?
Fine. Yes, brother.
Okay. So the second part, at full service load. So we have to calculate full service load. So there is only two differences here. First one, we have to calculate M total, the total movement. It would be MD, which we calculated previously, this one, plus MSD plus ML. So this MSD and ML would come from this 300 and 1000. This was superimposed dead and 1000 was live load. So this MSD would be 300 into L square over 8 and ML would be 1000 into L square over 8. So this way we can calculate M total. Secondly, we have to calculate effective pre-stress force. So that would be 0. R times PI. So R was 0.84 times PI. We can calculate PE or effective pre-stress force by this formula. Then the formulas are same, exactly same. F top and F bottom. Stress at top and stress at bottom. It would be bus minus PE over A. Only difference is PE. This one PE. The rest is same. PE over A 1 minus EC over R square and minus M total over S. These are two differences. Similarly, minus PE over AC 1 plus EC over R square and plus M total over L. Simply by changing these two values, we can calculate the stresses at full service load. And there are four conditions given. Hmm?
Brother, always in top.
Sorry,
Brother, always we should take minus in top and plus in bottom.
this sign, this
No
one sign.
brackets.
Yes, yes, this. Actually, this is like this. For example, this is our center of gravity of concrete. Center of gravity of concrete. And we have this tendon almost parabolically like this. So this force is like P and P. So this is acting at this sensitivity to the uh, center of gravity of concrete. So after it will produce hogging like this. So it produces uh, tension at top and compression at bottom, right? There is tension at top and compression at bottom. This produces opposite stresses. Actually, in sagging, we have compression at top but tension at bottom. But this pre-stress force produces tension at top and compression at bottom. So if we multiply this minus with this minus, this is actually plus. So this one force is tensile force. We have taken, you can say common, so it looks like it's negative, but it is actually plus. This is tensile force. So this is tensile force at the top. And similarly, this one becomes compression because due to superimposed dead load, it becomes like this, a little bit sagging. So compression at top and tension at bottom. So minus into plus, this was minus, and this is compression. Okay. We have to
Okay, brother.
just memorize these signs. You can just memorize.
Okay, brother.
Okay. So this one. So there are four limits set by CI that our stresses should not be in these limits. There was somewhere error. There are, you can find them on slides, but there are four limits: FCI, FTI. There are four initial pre-stress forces. This one is for initial pre-stress forces. For these one, there are top and bottom stresses should not be more than these two values for initial pre-stress. So this one is 0.6 times FCI dash. FCI dash was given in the question. This one 4000 psi. The concrete strength was 5000, but at the time of processing, it was 4000. So we have to take this FCI dash as 4000 and we should multiply it by 0.6. And our top and bottom stresses should not be more than these. Before application of load, these stresses before application of load should not be more than these 0.4 times FCI and 3 under root FCI. These are before application of load. And for after application, we have FC as 0.45 FC prime and FT tensile stresses should not be more than 6 under root FC prime. So they are written in the slides, but we have to memorize them also because we have to check our first two stresses should not be more than these and our last two stresses should not be more than these. So this is our check. Okay. Yes, this one here. FCI is maximum allowable compressive stress immediately after transfer and before losses. So it is 0.6 times and FTI is 300 FCI. Similarly, FC is 0.45 and FT is 600 FCI. So our stresses should not be more than these values. This is complete numerical. After calculation of these four stresses, and we have to check them. And if they are lying in these values, then our these stresses is okay. Otherwise, we have to revise. We don't not have to revise, but in field, if they are doing that, then we have to revise there. Actually, numerical or numerical is finished here. Okay, any issue in this? Or should we proceed this second?
Brother, in this type of numerical, only just these things we should do. It means just we need to calculate before applying the load and after applying load. After that, just we need to check it.
Yes, only these.
Okay,
First, we
brother.
have to calculate some parameters, then before and after, and then checking. Numerical is finished. So if this type of question comes, then we are given an I section and we have to calculate. So this is exactly similar, but the first step is different. That we have to calculate its moment inertia a bit differently and its area a bit differently. The rest of it is same, almost same. So if we have to calculate this area, we can make this an I section. This is 3 inches its depth and 20. They have given this one. This they have given its average height. So we can take this as rectangular also. This curve they have given us the average height. So we can also take it as rectangular one like this 3 inches, 20 inches, 10 inches and 6 inches. And 4 inches its thickness at middle and the height is total 30 inches. 4 inches and 30 inches. So this one would be 30 minus 3 minus 6, so 21 inches. So this is our dimension of I section. And they have also given us the centroid, 13.9 from the top and 16.1 from the bottom. So our centroid is 13.9 from top and 16.1 from bottom. So first we have to calculate same steps. First we have to calculate area of concrete. So it would be 20 times 3, 20 into 3, 60 plus this one 21 times 4, 21 times 4 plus the bottom rectangle 10 times 6 again 60. So we can calculate directly area of concrete by this. So for moment of inertia for this rectangle for the bottom one, this one for one, it is BDQ by 12. 10 into 6 cube by 12. This one is BD cube by 12 plus. We are using parallel access theorem. It says that summation I plus AY square is equal to moment of inertia. So summation individual moment of inertia plus 8 area times into distance from centroid. This y is distance from centroid. So this is individual moment of inertia of this bottom rectangle plus eta A. A is 10 into 6 again. This one into y square. So distance from centroid is this one. This is y1. So it would be 16.1. This one is 16.1 minus 6 by 2. This is half of this depth. So it will be 6 by 2. 16.1 minus 6 by 2 square. This is for the bottom rectangle. For the middle one, 4 into 21 cube by 12 plus 4 into 21. And the distance from this centroid to the total centroid of the shape is 16.1 minus this 6 minus half of this 21. This would be half of 21 because this would be 21 half. So this is 21 by 2. 21 by 2 whole square. Similarly for the third one, 20 into 3 cube by 12 plus 20 into 3 and 13.9 minus 3 half of 3. So this is how we can calculate the centroid of this I section. So simple by using parallel access theorem, we can use this. After that, we have CT. We have given as distance from neutral axis to the top fiber as 13.9. 13.9. And CB to the bottom fiber it is 16.1. So IT would be, sorry, IT ST. Section modulus at top fiber would be I over CT. Similarly, section modulus at bottom would be I over CB. So this is how we can calculate section modulus at top and bottom, and this, and of course R square would be I over A, the square of the gyration. This is how we can calculate all parameters, and simply after putting it F top and F bottom would be minus Pi over A before pre-stressing minus Pi over A. 1 minus EC over R square, and we have to use ET at here. Sorry, CT at here. The distance from top fiber. Similarly, 1 plus ECB over R square. So this one is the difference, and minus MD over ST minus MD over SB. So we have to use the corresponding section modulus. So this is the difference in this question. Only this one. The rest is the same. Any issue in this?
Brother, in here, in bottom part, we have to, you have put at minus MD over S. It should be minus or
sorry,
same as
sorry.
plus.
No, plus, sorry. These sign should be both same here and also here. I am
And
embarrassed by
also,
this that
okay, brother. And also in here, we should take that after applying force also,
yes,
or
yes.
on. Okay.
For the second part, we have to calculate concrete stresses at full service load. So this is actually part A, and we have to do also part B for full service load. And PE would be they have written time dependent losses of 20%. This means R is 80, 0.8. So PE would be 0.8 times PI. That there are 20% losses, so the remaining would be 80% is left. PI is given, and this R is and PE calculated. And we can calculate MD by similar gamma times area of concrete. We have area of concrete this one, and we can calculate by multiplying with gamma. So simply by multiplying with gamma, we can calculate the WD. From that, we can calculate MD, and we can use here MD, and live loads are given 400 and 425 similar. We can similarly add them, and we can calculate total moment. Fine. So for the last one, this is a bit different, that they have given us the sections 6-inch width and 20-inch depth was 20 and 6, and this we have FC prime as 4000 and FCI as 3000. The difference is only that we do not know PI and E. We have to calculate this PI and E. So for this, again same method, calculate AC, that is area of concrete. IC, this is modulus velocity. R is equal to IC over AC, and then here S is equal to IC over C. So C is, we have 20, half of 20, so that would be 10. C is equal to 10. So we can calculate these 4 parameters first. Then before apply, we know that before losses, this is F top and F bottom, again same. So PI over AC 1 minus EC over R square minus MD over S, PI over AC 1 plus EC over R square plus MD over S. So we know all these. We can calculate. We can put FT and FB. These are top and bottom stresses. So we can put top stress as 165. This one FTI 165, and bottom stress as 1800, negative 1800. Because this is compressor. This standard will try to pull like this. So tension would be at top and compression would be at bottom. So we are putting tension, the positive value as in the equation 1, and the negative value minus 1800, this is compression, in the equation 2. So we are putting this here. We do not know PI here and here, and we do not know E. So this would create two equations. First equation in this P and E, second equation in this P and E. So we have to solve both of these equations simultaneously. And after solving them simultaneously, we can calculate P and E. So if we are solving these simultaneously, we'll get P and E. This one was part first. The second part is saying that we have to calculate maximum superimposed dead load, superimposed moment. So for, for second, for part B, after losses, is saying that we have to calculate maximum superimposed dead load. So we can take MT as MD. MD we can calculate simply by gamma into AC. That would be omega, and omega L square over 8. We can calculate MD, but we do not know MSD plus M live. So we can take them as X. We can take that as X. So our equation would become F top and F bottom. Same equation, minus PE over AC minus PE over AC. 1 minus EC over R square, 1 plus EC over R square. The difference is this, that we have to write M total here. So we can write as MD plus X over S and plus MD plus X over S. So this X is unknown here. We know this forces. We can put them as 380 and 1800. 380 and 1800. So after application of dead load, we know that compression moves to top. Compression moves to top and tension moves to bottom after application and upload. So we have to put here minus 1800. This is important. And here the positive value. This one was 380. So before application of losses, we are putting tension at top and compression at bottom. But after losses have occurred, we are putting compression at top and tension at bottom. So we are reversing this. Tension moves from top before the losses to bottom after the losses. So we have to keep this in mind that where we have to put in, and we can get two values effects from both equations, one and second. So that smaller one, that would be our maximum value. That would be the maximum value, and we have to calculate this. Okay, any issues in this? This way we can calculate maximum moment. So this they are asking maximum moment.
Brother, while in before applying the load, okay, in that part, while we are finding the pi value, we should
Yes.
solve the equation with minus sign in front of pi or without minus sign.
With this one. Always this is always minus.
Okay, brother.
I forgot this one. Actually, equation remains same always. Always it is minus. It is compressive load. Okay, any more? Anything I missed? So this is actually all for pre-stressing. This is like all. If we quickly go through this one numerical example. So we have given all this thing. So only the difference is this, that they have not given us initial and final pre-stressing forces, but they have given us the area of steel. This one is area of steel, and we are given with initial and final initial and effective pre-stresses. So initial pre-stresses is 189. This is stress, and the final is 150 psi. So for low to calculate to convert this into forces, simply we have to multiply it with area. So after multiplying this with area, we can calculate initial and final pre-stress force. Same way we can calculate that moment, and applying the equation, we can calculate top stress, and this one is bottom stress. So we have checked this with the limit AC allowed limit. So it was falling in between, so it is okay. Similarly for service load, this is service moment, and we are adding this in the dead moment. So we are getting total moment. And similarly by putting the values, we can calculate top and bottom stresses. So this is all. Okay, should we move to UBC? Or any query in this?
No issues, Hamza.
Brother, this question is 10 marks question.
10 marks. Last time theory, sir gave us theory, it was of I think 5 marks. I don't think it would be of 10 marks. Maybe 6-7 marks. It is actually a small question. Only we have to memorize just these two formulas. This UBC one was, I think, also for 7-8 marks. We also have bridge engineering lectures, 2 lectures of bridge engineering. So some theory would be off from there too, 4 or 5 marks. So maybe 15 marks from this,
Okay, brother. Thanks.
and from 5 and 6 from that. So this is UBC. So we are designing our building according to, we are going to check that if our building is designed according to code or not. So for this, for example, this is problem one. It's given in slides. This is three-story concrete shear wall building. So first of all, we have to write all data in this. Data is important in this one. So three-story. First is three-story. Second is concrete shear wall. That our building contains concrete shear wall. Third is office building. What is its type? This is office building. We are going to get factor from all these. And its location is in their district. Location of this is in their district. And shear wave velocity is 3000. So velocity we have 3000 feet per second. So this is per location. And story heights are 13 feet and 11 feet. So we are three-story building. First is we have 13 feet and 11 feet and 11 feet. Load we have 2200 kips at bottom and 2017 at top. So 2200 at bottom, 2000 and 1700 at the first stories. So this is plan dimension. We do not need this, and wall we do not need this. So this is actually we need this all data. So after this data, we have to go to the UBC. Sir was saying that maybe factors would be given in the paper, but still to check them, we have to go to UBC. So you have to go to page number 30 of UBC code. This is 29 and 30. So from here we have to start. Page number 30 of UBC code. So first we have to go for occupancy category. That what is the importance of this building? So as this is office building, this is was office building. So its importance is 1. Importance factor is 1. For example, if it was a hospital or some emergency building or maybe a military building, so in that case, its importance would have been 1.25. Fire and police station, garages for emergency, and etc. So in only in those cases, our importance would be 1.25. Otherwise, we have all our buildings have importance of 1.0. So first we have to calculate importance. Second, we have to check the soil profiles. So we are given the shear wave velocity is 3000. So there is shear wave velocity column of shear wave velocity here. So 3000 fall between 2500 and 5000. So our soil profile would be SB. Second part would be our first one our important sector. Second is our soil profile. So it is SB soil. Similarly, we can be given that the n value for sand penetration test lies is 30. So we can check this as soil as ST soil. So this value was just given to categorize our soil of the look soil where our building is going to lie. And the third is zone factor. So for zone factor, we need the zone, and for zone, we need a map. We need to know where our location is. So the zone 1 is given in green, dark green. Zone 2 is in light green, 2B in yellow, 3 in orange, and 4 in red. So we have to check where is their district. So I know that it is in KPK, so here it is. Here it is upper and lower there. It is already pink, so this is the is it visible that here it is upper and lower there. So it is lying in orange region. So orange is zone 3. So we have to take zone 3 and our Z value would be 0.3. So the location is lying in zone 3, which means Z is equal to 0.3. So we have calculated this, and then we have to go a bit down and here. Structural system. What is the type of our building? So our building is concrete shear wall building. Our building is office building with shear wall. So we have a frame building and we have shear wall and it is concrete. So this is how we can calculate the R of this building. R would be 5.5. This comes from if we have a steel moment resisting frame, so we have to go from this moment resisting frame and we have to check steel and whether it is special moment resisting or ordinary moment resisting. It is given in the question. So if it was special moment resisting, our value of R would have been 8.5. So this is how we can calculate R value. So after R, we have to calculate CA and CB. CA and CB. So this is CA and CB. So we have zone 0.3, zone 3, and we have soil profile as SB. So our CA value would have been 0.3. Similarly, zone 3 and SB are so CB value is 0.3. They have same values. So CA is equal to 0.3, CV is equal to 0.3. So we have C and CV values. So if, for example, if considering our frame or building lied in zone 4, then we also have to check this seismic source type. If and only if in this question, this one, suppose in problem 2, our zone, this city of Muzaffarabad, it lies in zone 4. In zone 4. So for zone 4, we have to also check this table. This one seismic source type. So this is given in this question for problem 2 that it has moderate slip rate of 2 mm and magnitude of earthquake is greater than 7. So slip rate of 2 mm and magnitude is 7. So this one was this. That magnitude is greater than 7, but slip rate is 2, so which is less than 5. So our source type would have been seismic source type would have been B. And for B source type, we have to calculate NA. We are also given it is located 5 km from fault line. So for 5 km in seismic source type B, our NA would have been 1.2 and our NV would have been 1. NA would have been 1.0 and NV would have been 1.2. This way we can calculate NA and NV. It is only used in zone 4 and otherwise we do not need to check this. For zone 3 and below, we don't know to check it. Only we have to calculate C and CB. So we have to calculate these 5 parameters. Important factors, soil type, zone, and R and C and CB. Okay, any issue up till now?
Brother, in exams, they will provide these tables, or I think we are not allowed to bring these things.
No, we are not allowed, but I think last time sir have directly given us the values. Table were not given, but directly values were given. So we have to directly use them.
Okay, brother.
So after this, after calculating these values, first step of question would be we have to calculate seismic dead load. Seismic dead load. So zero dead load is W, and it is simply the dead load on all stories, summation of all dead loads from 200, 2000, and 1700. 20 to 40, 42, and 49, and 59. So our dead load would be 5900 kips. Simply this is dead load. If, for example, we were given like this, that this is 6, the frames are 6 feet apart, and the load is almost 420 pounds per foot, like in case of pre-stress concrete. So in this case, we have to multiply 420 by 6. That way we can calculate total dead load in this building, in this story, and add it to this one, and we can calculate total dead load. And if we were given area loads, like for example, this is PSF, 100 PSF, 100 pound per square feet, then we must have been given with the plan of this. For example, this is 100 feet by 100 feet. Then we have to multiply this 100 by this 100 and 100. So total load will be 100 times area, 100 into 100. So actually, you have to calculate load in terms of Newton or kVs or pounds. So we do not need any UDL or area load or something like that. We only need point load, like in units of simple loads. So this way we can calculate load. After load calculation, the second step would be base shear. We have to calculate base shear of our building. So three formulas are given for base shear. This one. The first one is base shear, the normal formula base shear. The second one is V maximum. What would be our maximum base shear? Third one is V minimum. So what is the least or minimum base shear we can take for some building? So we have to calculate all these three values. We have to also memorize them. Sir was saying that you would not be provided with formula. So we have to memorize these formula, and we have to use these three. If V was lying between V max and V minimum, it was in between these two values, then that's okay. Otherwise, if V was greater than V max, we have to use V max, and if V was lesser than V minimum, we have to use V minimum. I mean that our range of V would be between V maximum and V minimum. V cannot be greater than V maximum, or V cannot be lesser than V minimum. Fine. Then these three formulas we have to use. If it was zone 4, then this formula we have to also calculate. And in this we use NV, and that NV we have to calculate from table. So NV is only for zone 4. Okay. So this is how we can calculate base shear. Third one. Actually, we have to do this before time period. We should do time period before, because it is going to be used in base year. So time period I forgot before that we have to do this before. So it is CT time HN power raised to 3 by 4. Time period is CT HN 3 by 4. So this is CT and HN 3 by 4. HN is the total story height, total height of the building. Power and CT is factor. So it was steel movement resisting frame, it would be 0.035. For RC movement resisting frame, it is 0.03. And for all other type of building, if a building does not fall in the above two categories, we have to use CT as 0.02. So these values outside brackets are given in FPS. And this 0.0853, 0.031, and 0.048, these are given in SI units. So depending on the units, we have to use these values. Okay, fine. So this way we can calculate time period. And if our time period, this time period, if the time period is less than 0.7 second, if our time period was less than 0.7 second, our FT would have been 0. FT would have been 0. If the time period was greater than 0.7 second, and our FT would have been, we have to calculate FT by 0.07 TB. This formula. Calculate FT 0.07 TB. So what is FT? FT is concentrated force at top. For example, this is our building, and it has time period of 2 seconds. So if this is moving like this, so this is very time period 2 seconds means it is moving very slowly. That it is completing a cycle in a large time. So when the movement top is in this direction, the bottom is in this direction. So there is a difference of force between them. That top is moving like this, bottom is moving like this. So this would try to pull it backward, and we call it as a concentrated force at top. This force would make try to bring both the components together, top and bottom together. But since the time period is slow and time period is large, so the movement would be slow. So this force would try to bring it. It would not come actually, but it would try to bring it. So this is just formula. We have to use this formula. Ft is 0.07 TB. So we have to calculate this Ft like this. So after this calculation, we have to calculate the seismic dead, base shear, V. We calculate V max and V minimum, and time period. And if time period was less than 0.7, fine. If it was greater, then we have to calculate Ft also. After this calculation, we have to draw table. We have first write story. Story suppose 3, 2, 1, and we have to write its height hx. So the height of story 1 was 13 feet. The height of story 2 from base is 13 plus 11. That would be 24. And similarly, 24 plus 7 would be 35. So this is height hx from base, from the ground level. And wx is load acting on it. So it was 2200, 2000, and 1700. After this, we have to calculate wx into hx. Simple multiply these two columns. We can calculate wh into hx. We have to sum this wx into hx. What was its whatever its value? The next column is wx into hx over summation wx hx. So whatever the sum was, we have to divide this value by sum. This value was sum, this value was sum. Like this. This was hx. This is wx, wx hx, and wx hx over summation. So this column we get wx hx over summation, and the value the sum of this column should be 1. The total sum of this column should be 1. Fine. So we are calculating this wx hx. So after calculating this, the force Fx, the horizontal force at any story level, would be this factor multiplied by V. So this factor we have to multiply it by V. V was multiplied by V, then we get this value Fx. So what was V? V was our base here, this value. Simple, we have to multiply this factor with the V value. We'll get Fx. And Vx is simply summation of this. That summation we have to accumulate this Fx value. The first is the same. Fx and Vx is same. Second is 351 plus 289, we get 635. 635 plus 169, we get 805. So we have to accumulate Vx values, Fx values, and we get Vx values. So this is how we can get Vx values. The last value of Vx should be equal to what was our base here. For example, our base here was 1000. The last value of Vx should be 1000. It means our calculations are okay. Otherwise, we have done some mistake in some portion. And the last column is mx. Mx is overturning moment. So for mx, we have to draw our building. We have to rotate our building like this. Actually, our building is like this, and forces are acting like this. F1 at story 1, F2 at story 2, F3 at story 3. But we have to rotate this forces like this. This is F1, this is F2, this is F3. Forces at story. So between ground and story 1, the height was 13 feet, the rest was 11 feet. So for first moment we have 0 here. We do not have any movement here. Second moment we have F3 times 11. So whatever the value of F3 is, if you multiply it by 11, F3 was this one, story 3. Who says story 3? This is F3. This is F3. So if you multiply F3 by the height, we can calculate mx F3 into 11. Suppose for story 2, we have F3 into 22 plus F2 into 11. Similarly, like we did in bending moment diagram, F3 into 22 plus F2 into 11, like this. These 11 and 22 are simple story heights. They can be whatever the values. And the last one would be F3 into 35 plus F2 into 24 plus F3 F1 into 13. So this way we can calculate overturning moment. mx is overturning moment. Okay, so this is all for UBC. If we calculate, draw this table, that question is over. That's
Brother, I have one question. Can you please explain again that how to calculate fx value?
fx. Simple, multiply the factor wx hx over summation. This factor multiply
Yeah.
by v.
Okay.
V is the base here. We calculate the step 2. This one.
Okay. After
This
that,
one.
how to calculate vx?
Accumulate these fx values
Okay. Okay. Thank you.
like this. Okay, first is the same. Second is f2 plus v1. This is f3 plus v2. Similarly, just accumulate these values. We can get vx values. This is vx. This is fx. So, if for example, this was a case where ft is 0. The time period is less than 0.7. For example, if our time period was greater than 0.7, we obtained some value of ft. The only difference would have been in the topmost story, the story 3. After calculating fx, we have to just add ft also here. So only the difference would have been we have to add f3, ft at the top only. On all other directions or stories, it would have been the same. No difference there. So only add ft at the top. Not, no more difference at all. Okay. Should we proceed?
Yes, brother.
Okay, this one was for all UPC, and this is for exact calculation of time period. Here we use the formula CTHN power 3 by 4. This one, CTHN power 3 by 4. This is a empirical formula. We also have a thumb rule, that is story height by 10. Number of stories. The number of stories divided by 10. So if we have about 10 stories, we have time period of 1 second. This thumb rule tells us this thing. So if we have some exact data of stories, we can use this one. But if we want to make it more exact, we have to use this bigger one, this method B. So this method B, the example 3 is about method B. This example. So this is, but most probably it would not come, because for this sir was saying that we have to provide you with all these 3 values. This F1, F2, F3, they have come due to this. These are actually these values, these little forces. So these little forces we have to provide, sir have to provide us if this question comes. So most probably there are chances that it would not come, but it may be so. As factor of safety, we have to also prepare. So this is a 3-story building, and F1 is acting at the first story, F2 is acting as second story, and F3 is acting at the third story. So we have to calculate its exact time period. So for this, we are going to use stiffness method. So for example, this is our story, and this is our first story, this is our second story and third story. As first story, F1 is acting, second F2, and third F3. This would cause our building to sway like this, almost like this. Our building would bend like this. So at the story level 1, this we call as delta 1. At story level 2, we call this as delta 2. And the third one is delta 3. These are deflection at the stories. So for delta 1, we know the formula F is equal to Kx. Force is equal to stiffness times displacement. So displacement would be F over K. And for story 1, we have story 1. So what would be the total force acting on story 1? It would be actually the summation of F1, F2 and F3. All these three forces, the summation of these forces, they are acting on story 1. So F at story 1 would be F1 plus F2 plus F3. And the stiffness would be this one, K1, K2 and K3. Divided by K1, this one would give us delta 1. The deflection as story 1. So this we have F1, F2 and F3 divided by K1, and we can get deflection at story 1. This is delta 1. Okay, simple force over displacement. So at story 2, we have this displacement as delta 1. So this we have to calculate more. So this would be again same. At delta 2 would be delta 1 plus force over displacement. So the forces acting as story 2 would be F3 and F2 only. These the bottom forces do not act at the top ones. The top one acted at the bottom ones, but the bottom one do not act at the top ones. So F3 and F2 are acting. F2 plus F3 for stiffness of this story. This is K2. So simple delta 1 plus F2 plus F3 divided by K2. So this way you can get delta 2. This is delta 2. And exactly same way. This is delta 2. So this one would be delta 3 would be delta 2 plus F3 over K3. So this way we get calculate delta 3 and we agree to all the deflections. The formula was this one formula. So we need two terms. This is omega into delta square and F into delta. So omega is the load or the weight. So we can get we can make a column of omega into delta square and another column of F into delta. So omega into delta square for story 3, for story 2, for story 1. We can calculate the values, sum this, and for similarly F into delta, sum this. After summing this, put in the value here and take its under root, we can get the value of time period multiplied by 2p divided by g also. Like this. They have calculated this directly, but if suppose there were 5 or 6 stories, then it would become quite tedious like this. So just make columns and summation of weight into delta square, omega into delta square, and this is summation of F into delta, F into delta, and divide them with also G and take the square root and multiply it by 2 pi. We can calculate the time period as 0.724 seconds. Fine. Any issue in this?
No, brother, nothing.
Okay, so this was all the syllabus of Sir Burhan. Apart from theory. So
Abdul brother,
yes.
when we do the example number 1 and example number 2, when we find the time period through the empirical formula, CT
Yes.
value, it's available nearly 6 values. I mean 3 values in FPS and 3 values in SI standards. So do we need to memorize all of them? Do you think he will give?
No, actually, this one was given. This CT value was given. If we one moment, I have a previous papers. This one. So actually, CT was given in that paper. Also, the factors of all these factors from tables, they were also given, but the formula was not given. This like this. This is CT given. They have
CT.
given also these factors, but we have to memorize this formula. There is no formula given.
Yeah.
Actually, formula was also given, but sir was saying that this all the formulas were given. This formula sheet was provided with the paper, but sir was saying that they will not provide this time, so we have to memorize it. We would not be provided this time. So shear formulas we have to memorize. These values would most probably be given. Okay.
Okay, brother. Got it.
Okay. So this was all for this. So, do you want to do Sarasit today or?
If you have time, brother, maybe you are tired now, huh? Continuously you are taking, isn't it?
Yes, it's fine.
Okay, if it is fine, just briefly give us a small description regarding the frame.
Frame. Okay.
Yeah.
Actually, frame is exactly similar to beam. Have you done this beam one?
Yeah.
So it is exactly similar. For example, this one was. So if this frame. So we just ignore those frames with 3 members because for those frames we have too many unknowns, so we cannot solve them on calculator. So they will not come for 3 frame. But 2 element frame they may come like this one. And sir was actually saying in class that they may give like this one inclined member and one horizontal members. So for this, first we have to actually the steps for all this. First we have to calculate elemental stiffness matrix, the elemental stiffness matrix. Secondly, we have to calculate global stiffness matrix. We have to use direct stiffness method and calculate the global stiffness matrix from the elemental ones. On the third step, we have to apply boundary conditions. And in fourth step, we have to reduce the global stiffness matrix and find the reduced stiffness matrix. After reduced stiffness matrix, we have to simply take its inverse and multiply it by the force factor and calculate displacements. So after displacement, our sixth step was reactions. We calculated reactions before. But in the case of beam and frame, we do not need these reactions. We have to directly go to nodal forces. Because if we calculate nodal forces, we can calculate shear force diagram and bending moment diagram. And we can calculate from nodal forces reaction easily. So we do not need to do an extra step of calculate reactions. We can easily calculate them after calculating nodal forces. So this is the basic method. So first is elemental stiffness matrix. So we have two elements here. This element 1 and element 2. Element 1 is element 1. If it is element 1, it is connected between nodes 1 and 2. So it is u1, v1, phi1. Okay, in frame we have 3 degree of freedom. So at each node we have 3 unknowns. So we have 3 degree of freedom. So at node 1 we have u1, v1, phi1. Node 2, u2, v2, phi2. Okay, they have written this intelligently, I would say, that as at node 1, this is fixed port. So we have no displacement, no rotation, nothing here. And this is fixed port. So we do not need to write this u1, v1, phi1, u1, v1, phi1. So actually, these all will be cancelled in next step. So we don't need to write this. We can just write u2, v2, and phi2. So u2, v2, and phi2. And for frame case, we have to also memorize this one, this formula. This one, we have to memorize this part. That C1, 12, C2, 6, C and C2. This is actually if we for normal beam case for a for an axially loaded beam, axially transversely loaded beam, not axially. So for a simple beam case, the formula is 12, 6L, 6L, and 4L square. Right? This is the formula. So for 3 degree of freedom, just we have done this. That here it is C1, 0, 0, 0, 0. And this is 12 C2, 6L C2, 6L C2, and 4L square C2. And C1 is AE over L, axial stiffness of member, and C2 is EI over L cube. This is the you say stiffness axially, not I don't quite remember. So it had a name, axial stiffness, and yes, flexural stiffness. This is flexural stiffness against bending. So this is flexural stiffness. This is axial stiffness. So we have to memorize this one. C1 0 0. So here we have C1 0 0 0 0 and 12 C2, 12 C2, 6L C2, 6L C2, and 4L square C2. So just by this we can write the elemental stiffness matrix of element 1. So they have calculated E over L. If we take common E over L from this one and this one, so we can take a common this E over L outside. The only thing remaining here would be area, and here would be IC2 would be I over L square. So they have done this, that E over L they have taken outside, and they have multiplied. They have written area here, and we have just multiplied this. And for a second one, similarly here, this one is area. This is all those 6L and 12 and 6L, 6L and 4L square. So this one is it. Actually, this is different because they have transformed it at the same time. This was acting at no angle of 45 degrees. So they have transformed this at the same time. So for the transform, we have to use this formula. This one. The transform this one. This one would be provided. I was saying if a question of frame is in the paper, and this formula would be provided in that. Most probably this one will be provided. The second one we have to memorize. This one we have to memorize. This one. So for element 2, this was for element 2. So I forgot that element 1 was acting at an angle, so we have to use transformed stiffness matrix for that one. This one is untransformed. So this one is for element 2. Then K2 we can calculate like this. And for K1 we have to use this one, this formula. 6 your LS and L and S and C are sine and cosine. So S and C they have calculated before, and simple they plug in the values and calculate this. After calculating both stiffness matrices, we know the reduced stiffness equation would be. This is elemental stiffness matrix. Second is global. So we do not need to write full global stiffness matrix. It would be 9 by 9 because there's 3 degrees of freedom at each node. So it would be 9 by 9. But we do not need to write it. We can only write 3 by 3 at node 2, which are the unknowns. So at node 2, simple add the elemental stiffness matrix from 1 and 2. This one we obtain from element 1, and this one we obtain from element number 2. Simple. Simply, if we add these two, one, this and this, we get this global stiffness matrix, and it is actually reduced global stiffness matrix. We directly obtain this one, this one. So after this global stiffness matrix, third step is boundary condition. So we know that V1, Phi1, U1 all are 0. V2, V3, Phi3 and U3. These all are 0 because there are fixed port at these 2 points. These are 0. So these will be 0. So only thing would be left would be U2, V2 and Phi2. This thing. Only thing would be left this big U2, V2 and Phi2. So we need U2 for U2 we need F2x. For V2 we need F2y, and for Phi2 we need M2. So these are our unknowns times this is our reduced stiffness matrix U2, V2, Phi2. These are 3 unknowns. So what is the value of F2, F2 and M2? So we have a distributed load here. So if we have a distributed load, for example, this is our load. We have to convert this, whatever span is, we consider it is as fixed standard. Load is 1000. So we consider this as fixed standard span and 40 feet. So we go to this fixed standard charts. We calculate direction and movement of UDL. This one. We also have to memorize this one for simple UDL case, simple VDL case, and for 1 and 2 point loads. Sir was saying that we have to memorize for point loads acting at midspan, acting at 2/3. So there are 1 point load and 2 point load, and for full UDL and full VDL. This, and this, and for 2 point loads. This one. We have to memorize these 4 values. So for simple utility is quite easy. This is mega L by 2. This is mega L by 2. This is mega L square over 12. This is mega L square over 12. This is simple friction movements, friction interactions. Mega square by 12, 12, mega L by 2, mega L by 2. So this way we can calculate reactions. 1000 into 45 by 2. So 500. This is also 500. And similarly, suppose this is 50,000 and this is 50,000. So these are reactions. But for our nodal forces, we have to inverse them. These reactions were acting upwards. We have to take them as downward. So equivalent nodal forces. We have to inverse our reactions. So whatever the direction of our reactions were, we have to take the opposite one. This one was counterclockwise. We apply this as 50,000 suppose clockwise, and this one was clockwise. We make this as clockwise. So 50,000. So this way we can find the equivalent reactions of distributed loading. So this was our point number 2. This was our point number 3. So our F2y would be minus 22,500. This one. M2 is 50,000. And it is also negative because clockwise is negative here. Clockwise is negative. F3y is again minus 22,500. And M3 is positive because it is counterclockwise, so it is positive some value. I just suppose 50,000. So this way we can get the values. We have to plug in here. This was minus 22,500 or minus 22,500. No, actually F2x was 0. There was no force in horizontal direction. F2y was minus 22,500. M2 was M2 is minus 50,000. Is minus 50,000. So simply, if we plug in the values, we can calculate V2, Phi2 and U2. So if they plug in the values here, this they have found the values here. So after calculating the values, these values were in the global coordinate system. These are global coordinate system. So for the fourth step or R was after calculating the displacement, we had to calculate nodal forces. So for nodal forces, we do not need global. We need elemental or nodal displacement. We need elemental or nodal displacement. So we have to transform these global displacements into local ones. So the transformation matrix is the same. That is CS 0, 0, 0, 0, CS. Or we can also write it as it is simply this is CS minus SC. So this is our transformation matrix. So what we have to do is we have to transform U2, V2 and Phi2. So we know that for element 1 we have U1, V1, Phi1, U1, V1, Phi1, U2, V2, Phi2. So we have U1, V1, Phi1, 0, 0, 0. And U2, V2, Phi2, we have some values. So we know that this one actually see this. This is for this one. These 0.707, 0.707. These are for U2 and V2. This is not working here. So this one is for U2. This one 0.707. This into U2. This whole 4x4 matrix is for U2 and V2. For Phi2, we have used only one because we do not need to transform the rotation. It is in all coordinate system. It is same. We have used one for this Phi2, but these two for U1 and U2. Sorry, U2 and V2. For V1, U1 and Phi1, they were all 0. We do not need to actually write this one here. We only need this one. This 3 by 3 and this 3 matrix. This the top one we do not need this one. It all values will be 0 top here. So we'll get these 3 displacements in the local coordinate system. So after this, we can use this local coordinate system. The simple K times U1, V1, Phi1, U2, V2, Phi2. and these are in local coordinate system. This K is also this local coordinate system. This K is this one. This one, this is K. So this is the K, this is all the same. So simple multiplying this, we get the local forces, and this is not required actually because the element number 2 is the same in global and local ones. This element number 2 has the same coordinates in global and local ones. So this is not needed, but they are still written. This one or the same answer would be same. This is identity matrix. So this is for element number 2. We calculate these forces, and after these forces, these are all nodal forces. So these would be act along and parallel to these node elements. You can plot this like this. If we combine them, we can calculate the reactions and plot shear force and bending moment diagrams. Fine.
Yes.
Yes, brother. Alhamdulillah.
Brother, if we need to
Mhm.
practice that this type of problems, which questions will be good to practice?
Two elements only, because only
Okay,
two
brother.
elements could be solved. Three elements, I don't think. The variables are too much. I also need MATLAB for that.
Okay.
Yeah. So two elements would be enough, I think. So,
Thank you so much, brother.
okay.
Jazakallah khairan, brother.
Thank you so